When we do that, let's first simply go through some basic functions in our favorite reptilian programming language and see what we would use to describe some super basic random things. So let's go to the Jupyter notebook. So what we are going to use is a simple NumPy, some couple simple libraries, NumPy for generating the random numbers, and later on I'm going to use some visualization for which Matplotlib might be useful. So at first, if we want to, let's say, choose a random number, what people normally mean by random, they mean a number chosen from a uniform distribution. And what I mean by that, let's go to the graphs. So here I've chosen a lot of numbers from 0 to 1. And if we use the right function, when we choose a number from a uniform distribution, all of the numbers appear with the same frequency. So there's just as high of a probability to choose a small number close to the lower bound of the distribution as it is to choose a number near the higher bound. And how we do that in Python is we use a function uniform from NumPy random, and we describe the lower bound, the upper bound, and there's another argument that we can put in the function, which is the size. We'll leave it out for now. But let's say we want to generate a random number between -10 and 10, and this is what we would do. We would write this function. Each time it generates a random floating point number from -10 to 10. Sometimes we want to generate many numbers at once, then we use the size function. Let's say I want to generate 10 random numbers from -10 to 10, and this is what we get. So 10 numbers, yeah. So we would use this function, let's say, to choose a random spot on a street. So let's say we can describe, I don't know, Brivi street. Let's call one side of the street to be 0, and the other side of the street to be how many kilometers it is long. And we choose a random number between 0 and the number of kilometers, and that way we can randomly place ourselves on the street if that's something we want to do. Now, this is a nice distribution, but normally in our day-to-day lives, if we do things in random, chances are that there is some nice average value, which we do most of the time, and there are some smaller deviations. And to take that into account, we should use a normal distribution, which is also the so-called bell curve or Gaussian distribution, if you've heard of it. And the idea is simple, that your mean value, you're extremely likely to choose your mean value, and there are some deviations, and the bigger the deviation, the smaller the chance that you will do that deviation. For example, this might be the way you perform on a given task. So let's say, I don't know, your mental capabilities at one day, like you're really good at coding, and so you're doing, and you're doing something better than your average. And sometimes you're tired and you do worse than your average, but normally, most of the time, you would get your performance as being your average or mean. And to describe that, we use the function random normal, where the first argument is the mean value. So let's say I wanted to generate performance on, let's say, the default, I don't know, programming performance is 0, which is like, okay. And then we can, the second argument is the width of the distribution, like how variable are you in doing this task. So I could say, I don't know, the variability, the width of it is 3, and I want to generate a random number. So let's take out the size for now. and check what happens. So normally you would get randoms that are, numbers that are close to 0, but there is some variability. So sometimes you're like now, negative values, you're performing worse than usual. And sometimes there are positive numbers where you're performing better than usual, but on average is 0. And so we would use this this sort of distribution in all sorts of places in our day-to-day life. Like let's say we want to generate the heights of random people. We would use this distribution because well, there's the average height of a person, and then there are extremely tall people and extremely short people, but they are rarer to see. And similarly, we can add a size argument here to generate many such things. Okay, let's continue. 2 more things. It's not going to be, I think, too hard. So let's say I want to generate an event that might happen or might not happen. How can I tell a computer to do that? First, I define the probability of the event to happen. So I say, let's do one thing. I think it was, yes. So let's say I want to create an event that has 30% probability of happening. So what I do then is I produce luckiness, which is generated from a uniform distribution. Let's say from 0 to 1. So I generate luckiness, and let's say I get 0.22. So then I can check if my probability, which is I've defined here to be 0.3, that's arbitrary, if it is bigger than this luckiness I've generated, then the event takes place. If the luckiness I generated is bigger, let's say 0.75, then the probability, then the event will not take place. By doing this, we can see that around 30% of the time, I generate a random number between 0 and 1 that is smaller than the probability. Therefore, the event will take place 30% of the time. This is how we can tell computers to do that. And so here, just to test it out, okay, let's do it for, okay, let's do it for 5 at first. So I generate 5 instances where I want to see whether an event takes place. So I've generated 5 instances, and so then I check if the probability of this event being 30% is greater than the luckiness I've generated. So in the first instance, it is bigger, so the event takes place. In the second instance, the luckiness is bigger than the probability, therefore the event doesn't take place. Similarly, for the 3rd time, 4th time, and on the 5th time, the event again takes place. So, and if I do it, and I can sum up the true, false, 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 true. So this array, if I sum it up, trues get evaluated to 1s, and if I take the sum, then I get how many times the event takes place. So if I generate the event taking place 10 times, so here I set size to 10, then on average, I would expect, since the probability I've set is 30% or 0.3, then on average, I would expect that from these 10 times I've checked, 3 times of those, the event will take place. And so if I can click it many times, and you can see that the sum should average at around 3. In fact, if we don't print these out, I can try even bigger numbers, and it should be close to 30%. So now we're expecting something as around 30, and indeed, that is what we see. All right, and lastly, I think that we're going to need in the future is maybe we don't want to work with floats, maybe we want to work with integer numbers. In that case, there is a function random around int, which generates numbers similarly to the uniform distribution, all with equal frequency. Where all the numbers are integers from a lower bound to upper bound -1, because this is Python. So this function would generate numbers between 2 and 10, not 11. And again, you can add the size parameter. So if I want to generate 10 random integers from 2 to 10, I would do this. I could generate from -10 to 10, then I would write it like this. All right, that was a lengthy introduction into basic functions of generating random numbers in Python. Now, let's go to some applications. Yeah, so a question, how can we determine if a coin that's given to us is a fair coin? So we could try throwing it a lot of times, let's say, I don't know, 1,000,000. And if the coin lands heads 500,000 times around, then we would say that the coin is fair. How do we know that? Because the times it turned up heads versus the total times we used, like the total number of throws, that if the numbers are large enough, that should evaluate to approximately the probability of throwing heads. And this is precisely the idea of the so-called Monte Carlo simulations, where we define some probabilities of an event, let's say a coin flip, that being 0.5, and then we can simulate a coin flip using a computer. We make the computer throw the coin several times and see what happens, how many times it lands on heads, how many times it lands on tails, and we can infer things from that. And so the assignment of the probabilities to the event, the coin flip, that is called the model. It doesn't have to be a coin flip. It could be, I don't know, some random social interaction, for example. We can assign probabilities to that. Like, what's the probability that two people will meet? Or what's the probability that I will take a bike to work today instead of a bus? So these are all events to which we ascribe probabilities. Yeah, that's called the model. And from the model, using computers, we can infer interesting consequences. Let's examine that with the simple case of throwing a coin. So the model is that the probability of turning up heads is 0.5 or 50%. And we can predict some things from that using computers. So let's say someone asks you to calculate, okay, what's the probability that if I throw 5 coins, more than 3 heads would be among them in the results. You can take out a piece of paper and try to derive it yourself. It's sometimes not easy. And in real life applications, it gets even harder. Let's say you want to predict the way a fire would spread through a countryside. You can ascribe probabilities to different directions it might spread. Let's say there's a forest on one side and a field on the other side. So the fire spreading in a forest has a larger likelihood. So that's the model. And so the question is, like, could you calculate on a piece of paper where the fire would spread around? What's the which places should take some extra precaution? It might be hard, but for computers, we use that to describe it. And it's actually not that hard because computers are powerful. We do this. The idea is the same. We repeat the task many times and see what's the outcome, and then we can see what's the likelihood that fire spreads in that direction, and so on. So let's test it with a coin. So let's calculate the probability that more than 3 heads would turn up in 5 throws. So let's go back to the notebook. So here I've defined, so here, yeah, this small piece of code does that. So I've defined the probability of turning up heads as 50%. and I'm going to throw the coin 10,000 times. You can do it more. It just takes a little bit more time, and but the results are more precise. And so now we want to calculate the instances where more than three heads turn up. At first it's 0, but then we'll increment it and count the total number of cases. So then we have a loop. We throw the coin 10,000 times. We generate the, so yeah, we're throwing 5 coins at a time, right? So we generate 5 luckinesses. See, from 0 to 1, a random number from 0 to 1, 5 times. And then we check whether, similarly as before, here, then we check which of the luckinesses the probability of turning up heads is larger, and in those instances the coin is simulated to have fallen on heads. And then we sum up similarly also as before. Yeah, here we sum up this array where the 2 values correspond to the coin turning up heads. And if there are more than 3 heads, we increment the more than 3 heads counter. And at the end of the day, when we've done this 10,000 times, the probability of landing 3 heads in 5 throws equals simply the number of times it turned up more than 3 heads divided by the total number of trials. And we can check it, and we get that the result is approximately 0.18. Yeah, you see that it changes value from one simulation to the next, but this is the average. So we would expect that probability is 0.1819. Okay, cool. So now we can use this to predict some things in the world. But we can also go the other way around. Let's say someone gives you a coin, and you throw it several times. Yeah, you check that several times. If you throw 5 coins, then you see that on average, more than 3 heads turn up 0.4 or 40% of the time. So by doing that, you know that if the probability of 3 heads turning up in 5 throws is 0.4, your question might be, is it a fair coin? Maybe the probabilities have been skewed a bit. And in this instance, we have an observation, an experiment that we did in real life, and we want to update the model. What is the probability? So we're sort of working backwards. And this is also easily done using Monte Carlo simulations. So we can, again, go back to our notebook. So now we know that in real life, this probability is 0.4. Now the question is, what is the probability of throwing up, of throwing heads? We know that it's not 0.5 because in the case where the probability of throwing heads is 0.5, we get a smaller number for the probability of throwing more than 3 heads. So then we can check it out. We can iterate through different values of probabilities and see what we get. So if we take the probability of turning up heads and setting it smaller, we get the probability of getting 3 heads even smaller. Okay, sort of makes sense. So it must be bigger. So we can check bigger values, and we get bigger probabilities of getting 3 heads. And in fact, we can iterate through several values, and in the end, we get that it is best described by a value of throwing by a probability of throwing heads of 0.64. What it means that the friend that gave you this coin has given you a skewed coin, so don't gamble with him using this coin. Be careful. And in fact, we can also plot this. If you go through several different probabilities of turning up heads in that code, so we can change the input value. The probability of getting more than 3 heads follows this curve over here. So at first we started at 0.5 and we got around 0.2 probability of getting 3 heads. But empirically, by doing measurements, we saw that it was in fact around, 0. Okay, whatever. It was 0.4, and for that we got a value of 0.65. This line is a bit random. Okay, and so this is another insight that we can use. We can see observations, and we can work backwards to gather what are the probabilities that go into our model. And all this using the nice thing that our computer can generate a lot of random numbers in a short amount of time. I think a prototypical example where this works extremely nice is I think that's quite relevant to us right now, is the description of how pandemics spread. So you know that if one person is sick and another is healthy, they come into a contact, there is not 100% chance, like it's not guaranteed that they will transmit the disease. There is some probability associated, that there's also some probability to whether they meet, etc. So it's an inherently probabilistic process, and for that also we can use Monte Carlo simulations, and in fact some people do that. And this is our model. We can assign some given probabilities from educated, not educated guesses, from research. We can we can assign some probabilities for that happening, and then we can run our models. We can get predictions. We can get what's the probability that, I don't know, the infection would spread over there or over there, and how severe it is going to be. And and from that we can we can tell the results to the government. The government might enact some measures, and once the measures are enacted, people will act differently. The probabilities change, and we get some observations. So we empirically see, okay, the illness is progressing in a different manner than we first predicted. And then we can use this reverse process where we have our observations, and then we try to find the probabilities, let's say, of one person infecting another that match the observations. Then we can update our model. We can make the new predictions. We can then tell those predictions to the government or whatever. They could enact new measures and so on. So this is a sort of feedback loop that is used. Okay, one last thing I want to talk about is I remember when I was in high school, there were 2 people in my class that shared a birthday, and we were like around 30 people in the class. And you could, and I would think what's the chance of that happening? Odd, but yeah, it's interesting. And maybe if you look at your classes, try to recall whether there were some shared birthdays. In fact, that might be the case. I'm probably not the only one. And then you might ask, what is the probability? Like if you have around 30 people, the 2 of them share a birthday. At first it might seem a ridiculously small chance, because there are 365 days a year, and there are only 30 people. Why would 2 of them share a birthday? You could probably do the derivation on by hand, but that might be a bit tedious. So we can use the power of computers and try to simulate it using random numbers. And in fact, it's extremely, extremely easy. So here I tried to do that. So I said that the number of people that I'll be simulating are 30. And similarly as before, I'm going to check a lot of instances and try to take how many. Let's say I'm going to check 10,000 classrooms of 30 people, and I want to see what percentage of them have people that share birthdays. So here is a variable that will count the number of that will count from these 10,000 times the number of instances where some people share a birthday. So then I do a thing 10,000 times where I generate the birthdays of these people. So we can check what this function does. If you recall, this Okay, I haven't initialized it. This generates a random integer from 1 to 365. And that corresponds to the days of the year that a given person has a birthday. So here, this is the birthday distribution of the people in the class of 30 people. And then there's another interesting function from NumPy. It's unique. So what it does, let's say I have an array of, let's say 1, 1, 1, 2, 2, and 3. It strips away all the instances where an element of the array repeats. So the output of this is just 1, 2, and 3. Because it sees that there's a 1 here, it takes out these 2 ones because they repeat. And similarly, it takes out this 2 because it also repeats. So it gives, it returns an array with unique elements. And so if we use this on the array of birthdays, if there is a shared birthday, then the length of this returned array is going to be smaller than the original array. And so here we check if the length of the of this array, that's basically 30. Oh no, sorry, this one is basically 30. That's the length of the array of all birthdays. And if the length of unique birthdays with no repetitions is not equal to the length of the total birthdays, then that means that at least 2 people share a birthday, and we're going to increment this value, which counts the instances where 2 people share a birthday. And at the end of the day, when we do it many, many times, we say that the probability of 2 people sharing a birthday in a class of in this instance of 30 people is just the ratio of the instances where there is a shared birthday versus all of the trials. And similarly as tossing a coin. And then you get that the ratio for 30 people is around 0.7, or to put in other words, the probability of 2 people sharing a birthday in a 30 people classroom is 70%. So that's a lot. So it's more than 50% of the time. And again, we can try changing the classroom size. Let's say your class only had 20 people. Then the probability gets smaller, 0.4. And we can iterate through several values of people. And we would get this graph. So on the x-axis is the number of people in the classroom. And on the y-axis is the probability that a birthday is shared. And so here you can see that there are not a lot of people. The probability that there's a shared birthday is approximately 0. But around, I think it's 23 people, there is a 50% probability that 2 of them share a birthday, which is an interesting result. And by the time you get to 50, it's almost 100% chance. Now, and all of this can be calculated without explicitly evaluating some probabilities or doing some crazy math. It just, computer, here, take these probabilities, do it, do the calculations a lot of times and see what's the outcome. So it's super, super, super easy. It's like, yeah, the basic idea is you throw a coin many, many, many times and you calculate the successful results divided by the total attempts you tried. And that is it. That's the basic idea of this method. And it's really powerful. So what I want you to take away is that anytime you can generate some basic probabilities that you can assign to some elementary events. Let's say you want to calculate, I don't know, how an information spreads in some social network. So if you can estimate what's the probability of one person if they meet another person to spread this information forward, you can use then your super powerful computers to calculate what is the expected value, what are the implications, what is the result of the interactions between these probabilities. And you can use it in a lot of different scenarios. For example, you make a game that incorporates some RNG in it, and you want to calculate how difficult it's going to be for your players. You can also use Monte Carlo simulations. You just run it several times, let your computer crunch the numbers, and see what percentage of the time you get one result, what percentage of the time you get another result, what's the difficulty, for example, of some encounter in the game. Or you can also try to maximize the rate at which you show pop-up ads on your website to try not to drive away your visitors. If you can estimate the probability of your visitors leaving at a given annoyance level from the ads and so on. So it's a really powerful method. And I hope this inspires you to try and use it on your problems. And so I'm going to wrap it up and pass on the mic to my colleague, who will take you through a more complicated example than this toy model we were using of flipping coins. All right, maybe you have some questions. If not, I pass on the mic.
Hello, I will continue where Andres left off, and we will look at a more involved example. Because flipping coins is all nice, but it's not easy to apply that for real problems, or at least it may not be easy to see how to apply them. And the problem I propose to you is to determine the best strategy to arrange passengers in a queue in order to board a plane the fastest. This may be a real problem for airlines, as they want to optimize the time they spend doing important things like getting passengers on a plane. And it's a thing they might want to do very fast. To do that, we have to model a plane in a certain way. And I will try to share my screen. Give me a second. Yeah, should be sharing. Do you see my screen? Okay. So we could model a plane, as this is a simple and introductory simulation with a certain number of rows, for example, 5. And we could have seats at each side of the path or the aisle. One side we could call the plus seats, and another side we could call the minus seats. Usually in planes you have multiple seats at each side of the aisle, but that's more difficult to code in, so we'll stick with this simple plane. We could call it a super private jet, where you don't have to share your seat with anyone. So it may be a plane for rich people. And what you have in front of the plane is the queue, the passengers aligned in a queue. And we will model each passenger with a single number with the sign on it. So for example, here, the first passenger to enter the plane will be 5+, meaning that he wants to go to row 5 and to sit in a plus seat. So this one will go here. The 4- will go to the row 4 and seat minus, and so on. So they keep advancing, and we do this until the plane is full. So what strategies we could use to arrange the passengers so that they board the fastest? One could be random order, which is often used. Another thing you could try would be back first, where you have the back passengers boarding the first. So they reach the back, they seat, then you have the next row boarding, and so on. That could be another viable strategy. There could also be a front first strategy, where we seat the first row first, then only the second row, and so on. We may have some intuition that front first may not be faster than, for example, back first. But we can prove this by doing these Monte Carlo simulations and comparing the times with of boarding with these different strategies. So that's the setup of the simulation, and now we have to put this spotlighted your video for everyone. Not sure what that means. I presume I can continue. So we will continue to do this in Python, once again in Jupyter Notebooks. And I want to walk you through my code and show you how you could approach such a somewhat real simulation in code. Because what Andres did was all good and nice, but those examples were somewhat simple. And people would not probably pay money for you throwing 5 coins a million times. So I will walk you through my code, which will be shared afterwards as well, so you can play with it as well. So we will have some basic inputs, like a NumPy, this random module, and something for plotting. We will have a useful printing function, which we will see in action a bit later, but I do not want to get into this. It's just to print this state of the plane at a certain time for a in a human-friendly way. So what we will need before filling the plane, we'll have to say how many rows there are in the plane. We will have the people, the queue, where we, let me switch tabs. We will have to have an array for this queue where we will sort the people in a certain way. So that will be the people array. We can populate it with different numbers, and we'll see how everything looks. So this is the people list before shuffling. The example I'm using at the moment will be random ordering. So people are, this is the population of the array. There I shuffle it with the help of the random module. Then I will have another variable named path, which describes the state of the state of the path or the aisle. So in each of these, at a certain point, there may be a person, for example, 3 minus or minus 3, which will want to go to the row here and seat in the minus seat. And the state of the path will be described by the variable path. Another thing, we'll have to indicate that the seats are occupied or not. So we will have an array for plus seats and minus seats, which will be just points when they are empty. As you can see here as well, they are just points there. And I was not able to zoom in for some reason. Anyway, so that's the setup before we start boarding. We have arranged the people in a certain queue. Then we have to fill the plane. So I will walk you through what it looks like, and then we will see the logic of the code. So when we start boarding, the first thing that happens is that we are looking at a certain time. So time, 1 unit of time has passed. And we see here the model of the plane. So this is the one border of the plane. This is the other border of the plane. These are empty plus seats, empty minus seats, and this is the path or the aisle at the first moment in time. So what we see here is that the first passenger, +2, has entered the plane. Where he wants to get is the second row here and the plus seat. So he wants to get there. But walking there takes time. So in order to walk there, he will have to go here first. That will take 1 time step. So they have arrived at the second row, but in the meanwhile, another person has entered the plane, which is the -3 one. And they have to go to the row 3 and minus seat. While this person is seating, he will occupy the path for 1 unit as well, which we indicate by an S symbol, meaning that a person standing there is trying to sit down. This is not involving baggage yet as well, just sitting down, because we may assume that it takes non-zero time for you to get seated. And X means that the seat there is about to get occupied or is occupied already. And so we continue the simulation. We see the second person has sat down. We have the next time step. People keep advancing towards the back of the plane. The first person sits down. The -3 has gotten to the end of the plane, and so on. I hope the logic of the demonstration of the algorithm is clear. So people keep advancing to the end of the plane and they sit down whenever they can. So once again, the third one will come to the final row, the +1 will sit here. If we look at the next time step, time 8. So this guy was sitting there, the +3 has gotten to the end, and so on. And if we scroll all the way down, in the end, we see that the plane is full. All the seats are filled, indicated by the X's. We can quickly run through a longer example. For example, if I had 10 rows. So we can see the plane is now longer. There are 10 rows. So the +5 person keeps going until they get to the 5th row. Then they sit down and so on. We can see the plane slowly filling up. So the -7 keeps advancing to the 7th row and so on. Somehow we got, no, it's a random order, never mind. Anyway, so we see that filling a 10-row plane takes a bit longer than filling a 3-row plane, as you might expect if your intuition is not terrible. And we have filled the plane in the 38 units of time. So that was the visualization of the algorithm. And what I want to do is walk you through the logic of the code so that you can see that implementing these methods may not be as easy as flipping coins in a single line. No offense, Andres. I keep bashing you, but your examples were simpler and you know it. So what do we have? We have the path, meaning I'll go back to 3 rows. So we have the path, which was the empty aisle in the middle. And this pop function takes the last person of the people array, in this case 2, and puts it in the first position of the path. So that is the first time step, the first person boards the plane, so nothing special there. And what you saw previously here with all these nice and beautiful prints was this print state function that I did not want to get into. That's the output of this function that you saw below. So anyway, the first person gets into the plane, we start boarding. When the time unit has passed, we print the state, and then we start the simulation at time 2. So, and we will keep running the simulation until there is a person in the path, meaning that until everybody has sat down, there will always be a person in the path. So, and if a place in the path array is not occupied by anyone, it's represented by a 0. So in an empty plane, the path will be full of zeros. So this is my plane is boarded condition. Once the path is full of zeros, meaning that there are no people standing anymore, once the number of zeros is equal to the number of rows, the while cycle breaks and we have boarded the plane. Until that happens, the zeros will be less than the number of rows, so we will keep running this seating boarding logic. So at the beginning of every time step, we have the nice prints, these beautiful long lines with the current time. And what we do here, I think this first line, these 2 first lines are the hardest part in all of the code. So if you can get past these, the rest should be easy. So what I want to do with my path, I will insert a thing here. Path at time 2 equals 2, 0, 0. So this is the path at the very beginning of the simulation. As I have put the first person in the path, the 0th position of the path variable, I need this example here to walk you through the logic. So what I want to do is to iterate through this path, starting from the right side. So I have to iterate it through from its end, because these are the people, because these people will want to go to the right side of the plane if their ticket says them to go there. So, but before these people go, before the first people on the left can go, there have to be free spots on the right side. So I have to start the simulation from the right. And that's what I do here. This thing will iterate through numbers 0, 1, 2, when I have 3 rows. And then I will reverse those numbers to say 2, 1, 0, because I want to start iterating from the right side of the array. Maybe there's a better way to do this, but this was the solution I took. And if you are okay with this, then I think the rest of the simulation should be easy. So what I want to do is I look at the a point in the path starting from the right side, and I will name that the person. If this person is a 0, it means there's no one there, so I continue on. Continue in Python means that if you are inside the for cycle, continue restart the for cycle, ignoring the code after the continue statement. So if I see that the person is 0, for example here, the first one I will look at is a 0, I just restart the cycle and start again. And I take a look at the next person, which is once again a 0. So I will look at the first person finally. This part I explain later. And so what I see is that we have the person 2. 2 is obviously +2, not -2, meaning that this person has to get to the second row and to the plus seats. So what we have to do is compare whether the person has arrived at their seat already. If the position +1 is equal to the absolute value of the person's ticket. Why +1? Because Python indexes from 0, as we saw here, but people usually index from 1. So there is no 0 seat in a plane. The seats start at 1. So there is this +1 transition, which we have to compare. If that is the case, the person has arrived at their position, and their position in the path will now be replaced by S, indicating that the person there is being seated at the moment. As you could see here, for example, there was this +5 person who reached their spot. They are about to sit here, and then they occupied the path still because they are a bit slow while they sit down. So that's the S. And if the person's ticket says they're a positive person, they get to sit in the plus seats. If they're a negative person, they have to sit in the minus seats. Or that's the simulation at least. So that was if they have reached their position. Otherwise, if they still haven't reached their position, they have still to go. Their ticket says a bigger number than their current position, and the position in front of them of the path is empty, is a 0. Then they are able to move one step to the right, meaning that they free their current position of the path. It becomes a 0, indicating it's free. And the next step of the path becomes occupied by the person. So this indicates one step to the right direction. And it's basically the logic of the code. Take a look at the person. So take a look at the person. If there's no one, skip. If it's sitting, free up the position at the moment and start again. Once again, if the person has reached their spot, sit them down, occupy the seats, and if they have not reached their seat, keep them going if there is a free spot to go to, which may not always be the case. And I'm almost done with this engine of our game engine of boarding the plane, and then we can get to the results basically. And this thing is I have to occupy the first position of the path if it's empty, meaning that another person can board the plane. So I try to do that. I try to set the first position of the path array to people still standing outside the plane, but that may not always be possible, as people may have already been boarded in plane, so the people array will be empty. So this assignment would throw an error. It would not be possible because the people array is empty. In that case, I just ignore this and continue on. When this would happen is that people have boarded the plane, but they are still moving towards their seats. So this was the thing we had to include. And that's the logic of the boarding engine. And then we can put this into a board plane function. And then we can test it on different arrays of people, different ordering strategies to see how fast the plane could be boarded with a certain arrangement. So this is the same function you saw before, except I have commented out the print statements because I will run this function millions of times, and I don't want to keep printing because I have a small monitor. What we will test is different queuing strategies. For example, we have the random ordering, then we could order the people back first, front first, and then there are different back groups. I haven't finished the code. It will only take 1 second multiple times. So it's front first. So this back groups represents certain boarding groups. For example, I first board only the last 10 rows of the plane. Within this group, there's still randomness, but groups. So you see, we have the, I'll explain it in a second. So this is the random ordering, this is the back first ordering, front first ordering, and this is the boarding groups. You see, there are 2 groups at the moment, indicated by the 2 here. And in the first group boarding, there are only the last 2 rows of people arranged together. And the second group is the remaining front 2 rows. So this was the simple simulation where people have no baggage, which we could simulate. But this is not the main part of the code. I'd like to get on to the baggage part as well. But what we can see immediately that without baggage, back first rules over the random arrangement indicated by the random blue line. And front first is obviously terrible, as your intuition may have guessed in the beginning. Now there's this boarding with baggage. And this is the same code as before, except there are 2 additions. One, once the person has reached the row, we draw a random number from 1 to 0, and we compare it with a baggage probability, which I could say it's for example 90%. So this would represent 90% people having some baggage, and then we change their position to stowing away baggage, indicated by the B. If they don't have any baggage, they get immediately to seating. And if the person is stowing away their baggage, we add more time to the simulation, as it takes more time to stow away your baggage than just sitting down. So this is basically it. And at this point, finally, an important aspect of the presentation manifests itself. So here we start to use random numbers intensively, even for these front first, back first, apparently non-random orderings. There still may be variation in the boarding time due to the percentage of people having baggage. Some people are calling me, but I'm busy. So yeah, it's the same code as before, except we have added these baggage terms. So, and we can finally get to simulating these boarding times. And this is the last code cell of my simulation. So we are almost there. Since you have to show by example how to program, sometimes you have to do bad examples. And I think this is a kind of a bad example, because here I have done the same thing 5 times. I have 5 empty arrays. I have defined the parameters of my plane and the passengers. So 90% of people have baggage. Live coding, nice. And we have, for example, 150 rows in the plane. Start with something smaller so it runs faster. And I will run the simulation of the boarding 50 times here. So what I do is I initialize the people order by the init random function, and then I board the plane, and the function returns a certain time, which I then put in or append in the times array. And then I do it again. I initialize a different set of people, board the plane again, and I keep adding the times in these arrays. And finally, I will plot what we see here. So I run the simulation. It should take a couple of seconds. Oh, hard to tell anything there, but one thing we definitely see is that front first takes the most of time. We see The green line is way above the others. Yeah, in the middle, it's hard to tell which strategy is better. We would have to do some statistics on those results. But one thing we can also do is just make a plane longer. For example, not just 30 rows, because remember, we only have one seat on each side of the plane. So in a normal plane, you would have 30 rows of 3 seats on each side, meaning that it's a much bigger plane, for example, like a 100-row plane, an equivalent 100-row plane in this simulation here. If we run that, something different may emerge. Once again, it takes a couple of seconds. Yeah, you can already see the main conclusion of our talks. Monte Carlo is not always easy, but it's definitely powerful. Okay, so here we see an actual real-life conclusion. So front first is definitely terrible. Back first is not terrible, but not great as well. As we can see, even with all this randomness and 90% people having baggage, random boarding is always faster than this back first boarding. But we also introduced these boarding groups, which are hard to distinguish from one another, indicating that the size or the number of these groups may not be as important as having the groups in the first place. And I know, for example, the airline Lufthansa, they have these groups, usually 5 or something, meaning that they are operating near the maximum possible boarding times, which is good for them. But for example, Air Baltic, which is the national airline of Latvia, as far as I know, they don't have any boarding groups. They only do random boarding. And you see, the simulation indicates that it may not be the best strategy. You may want to introduce these boarding groups. And we can see that these random times, in this case, oscillate around 700, while the others with the groups oscillate around 650. So it's a 50-unit time increase, meaning that it's 50 over 700. It's 7% time increase of boarding if you introduce these boarding groups, which may be important for airlines. I'm not sure. For that, you would have to go to another talk. So yeah, this is the conclusion that we have simulated with these Monte Carlo methods on optimals. We have found an optimal strategy for boarding a plane, which could be a real life example. Of course, it's still a simple plane. We only have single seats on each side of the path. We could also do variation in the baggage stowing away times, in the seating times, in the moving times as well. So you could see these random fluctuations introduced at every aspect of boarding a plane. And this was a more involved simulation than just flipping a coin. Once again, sorry, Andres. But I feel like this indicates what you might do closer to real life with the Monte Carlo methods. So it's not easy, but it's very powerful. You would not be able to work out this optimal strategy on paper if you're a normal person, because on paper you can also do just finite computations as a computer does, but a computer is better at that. It takes less time for a computer to do it. So that's the end. Monte Carlo is not easy, but it is powerful. That's the main conclusion. Andres, maybe you have some final words as well, but it is powerful.
Nice. Yeah, I don't know if you have some questions, we are there to answer them. Yeah, I hope this inspires you to think about some randomness that you might apply in your own projects and use the inexhaustibility of computers to repeat the same task again and again and again.